The mastery of time. This is one of humankind's biggest obsessions. Since humans learned how to count, we've tried to understand and measure the observable phenomena of time. Whether past, present, or future, time is undoubtedly one of the most complex notions in our universe.
If we send satellites into space today, it's thanks to this rudimentary instrument, a stick that projects a shadow.
Over the centuries, making time has been the object of a perpetual scientific quest.
From the moment we control time, we control people.
Today, a group of experts made up of astrophysicists, engineers, and historians is following in the footsteps of these genius inventors who revolutionized our perception of time and of the world.
In fact, with relativity, Einstein showed that absolute rigid time does not exist.
The question Huygens posed was how to ensure that between each tick and tock, we always have 1 second. This epoch gave birth to extraordinary machines. Thanks to them, men have tamed the Earth's cycles. They escaped the ocean's traps, traced maps, secured transport, and built the foundations of our modern economy before launching clocks into space. Precious ally or formidable enemy, time dictates the rhythm of our lives.
At the fourth signal, it will be 21 hours and 46 minutes.
Perched on the heights of France's capital, the Paris Observatory looks like a sleeping ship. Yet within this secular institution is the heart of a machine that never stops beating. It is here that for 350 years, men and women have made our common time. This evening, the astrophysicist Pacom Delva is accompanied by Denis Savoy, science historian and specialist in time measurement. Like the astronomers of antiquity, the two scientists observe the movement of the stars, a sign of the passing of time.
Not yet. Ah, there's Saturn. You can really see the stars moving here. And when you look in the eyepiece, it's very obvious. If we don't use the motor to follow the movement of the sky, in fact, the planets move out of the eyepiece very quickly. So we really see time passing. This is linked to the Earth's rotation on itself. And as our position on Earth is fixed, we see the whole sky moving.
To find the origin of the measurement of time, we must go back to the prehistoric era.
The measurement of time begins with the first humans. We have no writings, but we suppose it was by observing the sun and the alternation of day and night. Then the discovery of the moon that illuminates the nights. And the moon resumes the same configuration after about 30 days. These two stars quickly become the masters of the division of time in the long term.
At its inception, The measurement of time was based on careful observation of natural phenomena. The survival of our distant ancestors depended closely on the position and rotation of the Earth in relation to the Sun. Thus, the day is devoted to hunting or gathering. At night, Paleolithic peoples protect themselves from the cold and predators while awaiting the return of the solar star. Before taming time, these nomads live according to the rhythm of nature and the seasons, synchronized to the cycle of plants or the movement of herds of herbivores.
The measurement of time is born with mathematic measurement, and certain testimonies claim it starts with the Babylonians and the Egyptians.
Here in Iraq, 3 millennia ago, the Babylonians living on the banks of the Euphrates left us a scientific legacy in the field of mathematics. Engraved within tight lines in cuneiform script, clay tablets reveal how Babylonian scholars divide the year into 12 months of 30 days. These first calendars, based on the cycles of the moon, make it possible to anticipate the return of the seasons, the periods of rain, and strong heat which return according to the lunar cycles.
Babylonian astronomy was extremely elaborate. They were able to predict in the long term the position of the sun, the moon, and the planets in the sky. They had what are called ephemeris. This means they have a perfect mastery of time. And this observation of time was done with the most rudimentary instrument of astronomy, the gnomon, which makes it possible to determine the fundamental constants of astronomy.
Denis Savoy is a specialist of gnomonics, the art of designing and tracing sundials. With this measuring instrument, the gnomon, Babylonian scientists measured time. Thanks to mathematics, this data enabled them to better control time.
This instrument dates back to ancient times, 2,000 years before Jesus Christ. If we send satellites into space today, it's thanks to this rudimentary instrument that projects a shadow. This gnomon is very simple. It's a stick that we plant vertically on a flat surface and we'll watch the end of the shadow. And throughout the day, at regular intervals, we use pebbles to mark the end of the shadow. We obtain a curve on the ground called a hyperbole, and we see there is a time of day when the shadow is the shortest. At this time, the sun is in the geographic south, at its highest. And this is where Babylonian astronomers measure the length of the shadow. And from the measurement of this length, they deduce parameters such as latitude, obliquity, length of the seasons, the solstice, etc.
The shadow of the gnomon shows that the Earth rotates both on itself and around the Sun, with an inclined axis of rotation. It is this inclination which causes the variation of the height of the Sun during the year, and which therefore causes the phenomenon of the seasons. Babylonian astronomers observed that at the winter solstice, the Sun is lowest in the sky and that it produces a very long shadow. At the summer solstice, the Sun is at its highest. It therefore produces a very short shadow. Scientists also note 2 periods during the year when the length of the days is equal to the length of the nights. These are the equinoxes. Thus, the solstices and the equinoxes divide the year into 4 periods: spring, summer, autumn, and winter.
We're starting to master these cycles, and time quickly becomes a major issue because it allows the forecasting of phenomena, the organization of society, of social life, of economic life. And from the moment we control time, we control people.
Ancient civilizations, like the Babylonians or the Egyptians, are therefore limited to the description of observable phenomena. It was not until the 5th century BC that scholars and Greek philosophers engaged in a new stage in the manufacture of time. They will manage to materialize the passing of time by inventing prodigious machines. In the alleys of central Athens, a tiny museum is dedicated to the technologies of ancient Greece. It is here that a former engineer reconstructed one of the most significant inventions of that era. The Clepsydra, meaning water thief in Greek, is the very first autonomous water clock. It is the work of a mechanical genius, Ctesibius of Alexandria.
I started my research in 1981. At the time, I was studying at Polytechnic in Athens. I'm a mechanical engineer. With the help of one of my teachers, I immersed myself in the technologies of ancient Greece. I looked for the sources of these extraordinary inventions, and little by little, I started to find solutions. The Ctesibius clock is an extraordinary invention. It's the first hydraulic clock. Our main source of research was inspired by the drawings of Vitruvius, a Roman architect, who described the inventions of Ctesibius. This water clock is truly admirable because it works with a gear system based on a ratio of 1 to 365. It has rods, cogs, and internal worm gears that Vitruvius describes in detail.
Ctesibius's Clepsydra consists of a system with 3 receptacles supplied by a water source and fitted with a piston operated with compressed air, a first of its kind. An ingenious cogwheel mechanism makes it possible to indicate the exact time, whatever the length of the day of year. The remains of this brilliant invention can be found in a little-known part of the Agora of Athens. This octagonal tower indicated the direction of the winds and housed Ctesibius's monumental clock.
The Tower of the Winds is revolutionary because it shows the time to the citizens. In each of the building's 8 sides, there were solar clocks, so the people of Athens could see both from the outside and the inside. From the outside when it was sunny, and in general Athens is sunny, but also from the inside at night and when there were clouds. Inside the Tower of the Winds, there was a system which was fed by water from outside the building. So it is a clock fed by a small source called the Clepsydra. It is a symbol of power. It shows the power of Athens, which has mastered time, and displays time to the Athenians and to the city's visitors.
To make public life uniform, the Greeks focused on time and developed instruments available to all to situate themselves in time. Throughout antiquity, people lived with unequal hours, which did not last 60 minutes as today. A day was split into 12 intervals. At the summer solstice, when the day is longest, the hour counts 80 minutes. On the other hand, in winter, as days are shorter, the hour is about 40 minutes. In the 3rd century BC, the Romans didn't take long to appropriate the inventions of Greek culture. Heirs to the gnomons, sundials are the basis of ancient Roman timekeeping. Sundials appear everywhere in the city and become common instruments. In the gardens of the Villa Borghese in Rome, one can still admire the inventions of that time, when the hour intervenes in many aspects of daily life, both private and public.
These sundials have a double function. A social function to indicate the time to the citizens, but they are also prestigious objects. This sculpted one in Villa Borghese is quite extraordinary. The owner wants to exhibit all his scientific knowledge and the sculpture that goes around it. They're not just scientific objects, they're also art, and we have to show off our wealth and knowledge. In general, there's a motto. Seneca had a beautiful one. We have very little time. We already lost a lot. And others are amusing, like, it's later than you think. These mottos evoke the passage of time from a philosophical and religious point of view. In Rome during the time of Augustus and Caesar, there are plenty of sundials, and people are complaining. They're used to eating when they're hungry, but now with sundials, they have to eat at noon on the dial. They're already prisoners of time.
Denis Savoy arrives at the Piazza di Monte Citereo. In front of the Italian Parliament stands an imposing monument, a vestige of Rome's greatness and of Roman scientific knowledge.
We're in front of the obelisk that Augustus brought back from the city of Heliopolis in Egypt to celebrate his victory over Egypt. And he places this obelisk on the Field of Mars in Rome, which will constitute a meridian. It's a gigantic gnomon, which indicates both solar noon and the date at the same time.
This 22-meter-high obelisk measures the lengthening or shortening of the days during the year. Archaeologists recently discovered that this monument, inaugurated 10 years before our era, was unique in its size in antiquity. Emperor Augustus placed the gigantic obelisk on a vast square paved with marble, about 500 feet by 230 feet. Astronomical graduations were traced on the ground, on the north-south axis, with bronze inscriptions, a few of which have been found.
It also serves as a calendar, because for the Romans, time is not just the hour, but also long-term time management of days and months. And we must remember that before Augustus, during Julius Caesar's rule, they already had a calendar, the Republican calendar, dating back to the 8th century BC. This calendar had the particularity that it was left to the favor of the pontiffs. And at the end of the year, they added a month or two to stay in line with the seasons. But what happens is this calendar becomes a means of political corruption. Depending on whether the pontiffs have friends or enemies in power, they lengthen or shorten the length of the year. And it arrives at such a cacophony that when Julius Caesar comes to power, they celebrate the harvest in the springtime.
Caesar wants to bring some order into the Roman agenda. The choices the emperor makes are not without consequences for our current calendar. He first decides that the year begins on January 1st. He then designates new months according to the names of the gods and goddesses. Januarius for Janus, god of beginnings and gates, becomes the month of January, or Junius for Juno, the goddess of family, becomes the month of June. The new calendar also makes references to Julius Caesar's family and his adopted son, with Julius and Augustus for the months of July and August.
The first thing Julius Caesar does is hire Sausigen, an astronomer, to reform this calendar, and then to bring the calendar back in line with the seasons. We'll have a year with 455 days. This is called the Year of Confusion. And he then established what is called the Julian calendar, which has a leap year every 4 years. This dates from 45 to 46 BC.
This is how Caesar created the longest year, a year of 15 months. After a flourishing ancient period in the field of instruments for measuring time, the race for accuracy continues considerably in the Muslim countries, with immense progress in the fields of mathematics, geometry, or physics. But in Europe, in the Christian world, this is not what will happen. In the late Middle Ages, in the 13th century, a mechanical invention will influence all humankind for ages to come. Preserved like a treasure, the astronomical clock of Bourges Cathedral is the work of Jean Fussoris, French astronomer and mathematician. Today, visitors to the cathedral can admire an intricate mechanism which not only tells the time, rings the bells, but also indicates the cycles of the moon and the sun.
We're inside Jean Fussoris' clock, and we can clearly see the folio here. This horizontal bar with the two masses which balance it. Here, the drive axis with two small pallets, and the escape wheel we see turning here, and the weight at the bottom that drives it all. It's extraordinary because it is practically the only one which is still in use in France.
This new generation mechanical clock has 3 essential parts: a weight, an escape wheel, and a verge escapement. The weight causes the needle to rotate. The escape wheel transmits the driving force of the weight to the cog. And the verge escapement, coupled to the escape wheel, serves as a horizontal balance. These beats are the units which give the fractions of time. This formidable technical innovation triggered a great vogue for mechanical clocks in the 14th century, all over Europe.
This system is really the beginning of clockmaking. It is an absolute splendor, and it will last until the 17th century with the invention of the pendulum clock by Christiaan Huygens.
Christiaan Huygens is a Dutch scientist who will put his genius at the service of the Sun King. A member of the Academy of Sciences, the young man attended the construction of the Paris Observatory in 1667. This institution was to become a major center of scientific conquest. We are in the Paris Observatory. It's one of the benchmarks of world time measurement. There are many in this race which will add more precision in timekeeping. And the instruments are built here. Experiments are made, clocks are tested, reports are made. We are in the very center of time measurement. With Huygens, we have clocks that we call high precision. Because Huygens was not only able to use the pendulum as a clock regulator, he was also able to maintain this regularity over time. The principle of this technical revolution is linked to two major innovations. The first is a pendulum, which under the effect of gravity makes a return trip once per second. This is its frequency. The second novelty is the lever escapement system, which allows the oscillations of the pendulum to be counted precisely. The biggest problem is constant isochronism. What does isochronism mean? Isos means equal, and chronos means time. So the question Huygens asked himself was how to make sure that between the tick and tock, we always have 1 second, and that all ticks and tocks are equal. Christiaan Huygens seems to have befriended Louis XIV. In 1673, he dedicated his last work to him on watchmaking mechanics. Invited to Versailles a few years earlier, Huygens presented the Sun King with his latest invention, a clock driven by a pendulum whose beat seems eternal. He explained to the amazed court that thanks to this pendulum, the timepiece only advances or lags by 15 seconds a day. It is a veritable leap forward in the race for precision. Huygens is convinced that we can determine our longitudinal position with precision using precise clocks. Galileo believed that a precision clock, or an instrument for measuring time, was an instrument for accompanying astronomical observations, and that the solution was in astronomical observations. But Huygens was convinced that if he found a way to take timekeeping with him on a boat, he would solve the problem of determining longitude. To find your exact bearings on the Earth's surface, you need to know two coordinates: latitude and longitude, which determine the angle between our position and a reference meridian like that of Paris or Greenwich. For latitude, it is possible to locate yourself in relation to the pole star, always fixed in the sky of the northern hemisphere. But longitude requires comparing the time on the meridian of origin to that of the place where we presently are. A difference of 4 minutes corresponds to 1 degree of longitude, or about 100 kilometers on the equator. At the time, onboard clocks did not withstand sea travel. Roll, pitch, and dust disrupted them. Thus, navigators did not have a reliable means on board to determine their longitudinal position. Despite several promising experiments with Christiaan Huygens clocks on board French Navy ships, the 17th century ended without finding a solution to the question of measurement of longitude. For most scientists, it even appears to be unanswerable. But the English have not yet said their last word. The scientific battle for longitudes is being fought from Greenwich Observatory in London. It It is on this hill that the famous meridian was drawn, and that in 1675, Greenwich Mean Time, the average time of Greenwich, was established. It was also here that we maintain the memory of a drama that turned the history of time upside down.
One of Britain's greatest naval disasters occurred in 1707 on the 22nd of October. Sir Cloudesley Shovel, who had been stationed in the Mediterranean, sailed back to England and lost 4 of his ships on the islands of Scilly, including himself. Approximately 1,400 to 2,000 lives were lost. The charts were incorrect, their navigational calculations were incorrect, their latitude had not been correctly observed, and the islands were positioned 50 miles northwards on the charts of where they actually were. This did bring to Britain, to the public, the enormous problems that sailors faced at sea.
Following this maritime disaster, in 1714, the British Admiralty launched a competition for scientists and watchmakers so that they could develop the first marine clock capable of giving the correct longitude without error.
The reward was in a tier system, so the more accurate your longitude determinations were by your method, the more money you would get for your efforts. So the biggest reward that the board offered was £20,000 if you could determine the longitude within half a degree or within 30 geographical miles.
In 1730, a genius clockmaker will take up the challenge. After inventing high-performance wooden mechanisms for the period, John Harrison dedicated himself to the design of a perfectly precise marine chronometer. The famous navigator James Cook would later be the first to experience Harrison's timepieces on his travels around the world.
The greatest challenges for a clock to work at sea, or a marine timekeeper, was it had to be able to deal with the motion of the vessel. It had to deal with quite extreme temperature variations, and it had to deal with the problem of oil, because any clock that's going to run for a long period of time, the oil would prevent it from keeping its accuracy. So Harrison's designs are based on the theory of a pendulum clock. The power is a mainspring. He devised a self-maintaining power system so that the clocks wouldn't run down when they were wound up. That's one of Harrison's great inventions. The other thing that Harrison did was he made 2 barbell constructions that worked simultaneously, so any movement would be counteracted by the movement on the opposite ends. They were connected with springs, which Harrison called artificial gravity.
In 1736, John Harrison embarks on an English Navy ship with his sea clock for a crossing to Lisbon. This trip is a test for the Commission of Longitudes. But his chronometer reacted very badly in the difficult conditions at sea. It was impossible for him to obtain reliable calculations, which would have allowed the ship to determine its position on the nautical charts. Once in Portugal, however, the clockmaker doesn't give up. He knows his invention needs some fine-tuning. On the return trip to Portsmouth, Harrison finally calculates the exact position of the ship. The success of his trip earned him a scholarship of £500.
Having a longitude method wasn't going to give them the edge over other countries. They already had that. It was just quicker, cheaper, more efficient. So it was an economic thing, really. It would give them an economic benefit in trade.
Over the next 30 years, Harrison will not stop perfecting his clock. John Harrison won the Royal Admiralty Award, but he was followed in Paris by a French clockmaker, Ferdinand Berthoud, who managed to design his own chronometer, thus determining a geographical position on land or at sea is inseparable from the measurement of time. The more precise this measurement, the more accurate our positioning will be. But to achieve this level of accuracy, it is still necessary to benefit from a common timescale, a universal temporal language. In other words, the same time for all, standard and unified. In the early 19th century, while the world still lives according to solar time, the Industrial Revolution radically changes our perception of time. With the invention of the railway, engineers will have to overcome a major obstacle: how to carry travelers on different timescales across countries. There are church sundials, station clocks, hours of astronomical observatories. But which schedule will be the standard? Travelers never stop adjusting their watches. As for locomotive engineers, despite their hourly indicators, they are never immune to a delay due to a breakdown or an unforeseen event, which always leads to more confusion. In the United States, a passenger crossing the country must reset his watch 75 times. One day in August 1883, a train left Providence City on the East Coast, traveling north. At the same time, at the other end of the railway line, a train leaves a station heading south. The two locomotives are going at full speed on a single track. The engineers have the same schedules, but do not have the same time on their watch. In a blind curve, the two trains collide, creating a twisted tragedy of metal. The toll is terrible: 14 dead and 17 injured. After numerous accidents of this kind all over the world, synchronizing railway clocks becomes a priority. In 1884, after heated exchanges, particularly between France and the United States, the Washington Conference chose the Greenwich meridian as a reference for the creation of a system of time zones. It is the one we know today. Paradoxically, it's at this moment that our conception of time, which passes in an identical way for everyone, will be radically called into question. Astrophysicist Pacom Delva is an heir to this revolution in Switzerland more than 100 years ago by modern physics, when Albert Einstein published his theory of relativity.
It's funny because during that period, we were trying to harmonize the same time for everyone, for France's railway stations and around the world. Einstein with relativity showed us that absolute rigid time does not exist. And that's what relativity actually shows us, that everyone has their own time. And so it's paradoxical, because today we have this illusion that we all have the same time. But in fact, it's virtual. It's fabricated.
This cyclist has the impression that the city is passing by her. But we can just as well say that the motionless spectators in this scene have the impression that it is the bike that's scrolling by. These two equivalent perceptions describe the principle of relativity. Likewise, Albert Einstein declares that this impression of passing time is explained by our displacement in space-time. In order to explain the genesis of this innovative theory, Pacom Delva goes to the places that served as young Einstein's laboratory, in a manner of speaking. So you have to imagine it's 1905. Albert Einstein lives just a little below here. To go to work at the patent office, which is a little further north, He always passed by here and saw the clock tower. And so he's confronted with certain questions of time, the nature of time, etc. In 1905, the public clocks in Bern were electronically coordinated for 15 years already. Albert Einstein had been studying the patents relating to time synchronization for 3 years. And then one day, the young man has a revelation. Absolute simultaneity does not exist. Two simultaneous events for one observer are not necessarily the same for another observer.
Those who preceded us and those who preceded Albert Einstein have all contributed elements. And for me, it's really a common work where sometimes a genius like Einstein will come to add a touch, and he'll succeed with the synthesis of various theories of his era. And he makes a leap in understanding. While other people cling to older ideas, staying in tradition, they can't make that conceptual leap. But Einstein manages to do it, like Kepler did before him, like Galileo and other greats. They managed to create something new.
Like Galileo, who describes that all bodies fall at the same speed in a vacuum, whatever their mass, physics sometimes progresses against common sense. Einstein's theory of relativity is no exception to this rule.
Albert Einstein made many thought experiments. We can also do a thought experiment like Einstein. Suppose I ask a friend to come with me to Bern. We take the train in Paris, but we don't take the same train. I'll take a high-speed train, which will arrive in Bern fairly quickly, as quickly as possible. My friend takes a much slower train. It will arrive later. In Paris, we take two very precise watches, like those we make today with atomic clocks, and we synchronize them. We put the same time on each watch in Paris before leaving. I arrive much faster than him in Bern, and once in Bern, I wait for him. I wait for his train, which goes much slower. And once it arrives, we compare our watches. Well, the time that elapsed between these two events, the departure from Paris when I synchronized my watch with my friend, and the arrival of my friend in Bern, when we recompared our watches, between these two events, we don't have the same durations, because our two trains did not go at the same speed. The difference on the watches will be a fraction of a nanosecond.
With Einstein, it's the end of the great universal beat, translated by the ticking of clocks. Physicists will gradually take the reins to impose a conventional and purely manufactured time with full knowledge. In a world launched headlong into the quest for even greater precision, physicists in Einstein's wake will soon rethink our machines to manufacture time. At the Paris Observatory, you can still contemplate the mechanical instruments that revolutionized their time. Protected under their glass bells, here are the ancestors of our quartz clocks.
From the 1930s, we will have extremely precise clocks. An astronomer who worked here, Nicholas Stoiko, will notice that there is a drift between the moment of a star's passage to the meridian and the time given by the clock. These are very precise pendulum clocks, and compared to the time given by the quartz clock at the Berlin Observatory, we will find that the Earth seems to slow down in spring and accelerate in autumn. And he comes to understand that this slowing down and acceleration of the Earth's rotation is due to the trade winds. And so it dealt a fatal blow at the end of the 1950s to the standard of time. From now on, astronomers will lose time management to the benefit of physicists.
By searching for what is most regular in nature, the movement of an electron in an atom, scientists invent the era of the measurement of atomic time. It is in one of these ancient astronomical domes that one of the most secret laboratories of the Paris Observatory is hidden. Astrophysicist Pacom Delva and his team monitor the proper functioning of one of the 5 atomic fountains in France. This type of clock, which produces our official universal time, is based on the vibration of the cesium atom.
That's the cesium cell, with 1 gram of cesium. From this atom, we will define what is 1 second.
When an atom is bombarded with energy, it vibrates. It emits more than 9 billion magnetic pulses per second. Each time one arrives at the precise number of 9,192,631,770 beats, 1 second has elapsed. So the seconds follow each other in an infinite manner.
When we say that this clock is exact, it means that we can certify that the frequency we get today will be the same as next year, or in 10 years, or in 100 years.
Today, the Paris Observatory is not only responsible for creating French legal time, its mission is also to distribute it. This takes place in an ultra-protected room where scientists watch over our time 24 hours a day. At the 4th signal, it will be 21 hours and 51 minutes.
Here we're in the National Time Reference Room, where French legal time is made from the signals of the clocks in the laboratory. We're going to synthesize French legal time with all these machines. Then we compare this legal time to other times in other countries. And from all these times, we will synthesize a global time, which is called UTC. And from this UTC, which will be referenced in Greenwich, we will add a certain number of hours depending on the time zone where we are. When a second passes here on this clock, it's the same second at the same time which passes in the United States, Japan, China, and Russia, etc.
Even a very precise clock is not enough to establish a reference time. This is why this time broadcasting room is linked with other clocks located abroad or in space on board a satellite.
These 2 antennas here send an electromagnetic signal into space towards a geostationary satellite, meaning it remains fixed in the sky. And from these comparisons, we're going to create a common time that will be the same for everyone, on all continents, in all countries.
Once it was onboard ships. Nowadays, clocks navigate in space. The acceleration of time that we sometimes feel is thus the consequence of a fabrication of the same hour for all. A conventional, synchronized, and increasingly precise time. This time, made by ultra-powerful computers, has even become the key for all the applications in a digital world. Whether it's our satellite-guided trips, our telecommunications, which use even more data on synchronized networks, or our banking transactions, for which every millisecond is worth millions. Our interconnected world is now based on clocks that measure times even more precisely, with enormous industrial and economic challenges as a result. We have become dependent, even slaves, to these new temporal norms.
Veritas filia temporis, the truth, daughter of time. To understand today's astronomy, today's challenges, you have to go back to the past. It's astonishing that at the time of the atomic clock and GPS, we can never forget that we are heirs to all these astronomers, and that our current division of time stems from human observations and from mathematical theories. Understanding ancient times helps shed light on today's science and modern astronomy.
From now on, and with every passing second, we remember the geniuses who tried to unravel one of the greatest mysteries of our existence. Einstein, Huygens, Galileo, Fusari's, or even Ctesibius, they all in their own way shaped the temporal language that brings us together today.